Hello everyone and welcome back. Today we're going to be speaking about mirrors, and more precisely we'll be speaking about planar and concave mirrors. Convex, we're going to leave it for another video. So, one of the properties that we spoke about waves is that they exhibit wavefronts. So wavefronts are simply waves that are in phase with respect to each other. As you can see from the picture, the crest and the troughs correspond perfectly around a pulsating sphere. Now, the way we represent wavefronts in physics, it is going to be through light rays. So light rays, they're always perpendicular to the wave fronts. So now, let's talk about the law of reflection and what it entails. It simply says that the angle of incidence always equals the angle of reflection. But before we continue with this statement, let's first look at what happens when light simply strikes a boundary. So we're going to go to our sketchbook and we're going to see the two different scenarios. The two different scenarios we're going to see in this class are going to be for opaque objects and for transparent objects. So as we said, we have a boundary. A boundary always separates two mediums. In this case, it is going to be medium number one, meaning material number one, whatever that is. And of course, it's going to be medium number two, and they're separated by this boundary. So we're going to have an incident light ray. The incident light ray is simply a light ray that originates within a medium and it's incident upon a surface, and it strikes the surface. If the object is opaque, meaning we cannot see through the other side, that is because we simply cannot, light rays do not pass through it. So what happens when an incident light ray strikes a boundary in a surface? One of two things are going to happen. Some of the light rays are going to be reflected, so they're going to bounce back within, and they're going to stay within the same medium, so they're going to be reflected, and some other ones are simply going to be absorbed. They're going to be absorbed by the particles that make up this substance, because the vibrational frequencies of the light will match the vibrational frequencies of the particles, and they're going to absorb them. That is the property of resonance. So now, if we have an opaque object, the reflected light rays are what we are going to see and perceive as that color. And the ones that get absorbed, we will not observe that color, because the reflected light rays are the ones that are going to reach our eye and they will appear to us as that color. So for example, imagine we have an object and it's green in color. So what does that mean? It means that the original incident light ray of light had all the mixture and the frequencies of all colors. That's why it was white light, and only the ones that reflected with green and entered our eye, and all the other ones were simply absorbed by the new medium. So that's what happens when the object is opaque. Now let's talk about when it is transparent. So transparency obviously means when light rays can now cross the boundary. So here's our boundary again. We have medium number one, and we have medium number two. In other words, we simply have different materials. And now we have an incident light ray, and it strikes the surface. So now what happens? Some of the light rays from the incident will now be reflected. So we're going to have reflected light rays, but certain other ones are now going to go inside the new medium, and they're going to be called refracted light rays, as you see right in front of you. And of course, we also have a third kind, which we're not going to go into it, and it's called translucent. It is simply a ratio between reflected and refracted. So let's say we have to talk about now the law of reflection. So we have the boundary, we have now medium one, and we have medium two, by which the mirror is made up of. So always the angles are given with respect to what is called the normal. The normal is an imaginary line that is always perpendicular to the boundary. It's always perpendicular to the surface. So it's 90 degrees. So the law of reflection simply states the following, that, let's say for example, we have an incident light ray, and it's going to form an angle with the normal. And again, it's always with respect to the normal. So theta 1, the angle of incidence, it's always going to be equal theta r, the angle of reflection. So the law of reflection simply says theta I equals theta R. Angle of incidence equals angle of reflection. So now let's go back to our presentation and let's see what happens. So as you can see right over here, we have an incident light ray. It strikes this surface of the mirror, and all the light rays now get reflected, because that's what a mirror simply does. The angle of incidence always equals the angle of reflection. We have two different types of reflection. We have specular reflection and diffuse reflection. Specular reflection, all the light rays are parallel with respect to each other, whereas diffuse reflection, we have different angles of reflection all around. So let's say we have an object, or in this case, a person standing in front of a mirror. The image that's going to be produced is going to have three properties. Number one, it's going to be upright. It's going to be, number two, it's going to be the same size of the object. In this case, it's going to be the same size as the person. And number three, the image is going to be as far behind the mirror as simply the person standing in front of it. So in other words, they're going to be equidistant. So one of the things that you must understand is that the image being created by a planar mirror is that it's a virtual image, meaning that the image appears to originate from behind the mirror itself. The reason why is, of course, the theory of the angle of reflection equaling the angle of incidence. So it always makes it appear as if the object originates from behind the mirror. And you can see over here, just by looking at geometry, you can see that it's going to be equidistant, the image from the object from the mirror. So that's planar mirrors. So you need to know and you need to memorize the three, different types that we just described, properties of planar mirror. So now, imagine we have a spherical mirror. The inside portion, let's say we take a small piece of the spherical mirror out now. The inside portion, the inside mirror is going to be a concave mirror, and the outside is going to be convex. The law of reflection still applies just like it does for a planar mirror. So, the first thing you must do when you're talking about a concave mirror is you have to draw the principal axis. The principal axis is a theoretical line that goes straight from the center, passes through something called a focal point, which we're going to discuss in a little bit, and then, of course, the midpoint of the mirror. So it's got to pass through all 3 points. So the focal point is basically where all the light rays will basically converge. So as you can see right over there, we have C, the center, and we have a certain point where all the light rays will basically cross from it. That is called the focal point. So the light rays that are parallel to the principal axis are reflected from the concave mirror and converge, as we said, to the focal point. And the distance between the focal point and the mirror is now called the focal length. The focal length is always 1/2 the distance of the radius. So you can see over here, C is the center, that's the radius. Halfway there is going to be the focal point. Spherical aberration, you don't need to know that much about it, but if all the light rays are not parallel to a single point, they do not pass to the focal point, it is called spherical aberration. You don't need to know that. This has many different applications. So for example, we can concentrate light rays on a particular point, as you can see in the picture, and we can actually warm up a certain liquid, for something that we need to use, so on and so forth. Now, if it's a convex mirror, the image is going to appear to originate from behind it. So at that point, for a convex mirror, the focal point will always be negative, and it's always going to appear on the other side. But more on that later. So let's now learn how to draw, light ray diagrams using concave mirrors. Always, 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 you must use 3 rays in order to make a ray diagram. So how are you going to do this? All 3 rays are going to originate from the same point on the object. So the first light ray is going to originate from the object. Let's say in this case the tip of the object. As you can see, we have an arrow. You're going to draw it parallel to the principal axis, and then you're going to reflect it to the mirror, and it's got to pass through the focal point. So that's the first one. The second one is now exactly the opposite. The light ray now passes through the focal point, goes to the mirror, and then reflects parallel to the principal axis as we just discussed. And then finally, the third light ray travels along a line that passes through the center. So in other words, you're going to draw again from the tip of the arrow. It's going to go to the mirror, it's going to reflect backwards, and it's got to pass through the center axis. And where all three of those lines, light rays meet, that's where the image is going to form. So you have to know the three different, and you have to memorize the three different possibilities. Where the object forms and what happens to the image and where does that form. In our first case, we have, as you can see, the object between the center and the focal point. So what can you guys see? The object that is going to be generated, it's a real image. It's always going to appear beyond the center, meaning the radius. It's going to be inverted, and it's always going to be enlarged. You have to know that when the image appears to be in front of the mirror, it's always going to be a real image. And in case of planar mirror we just discussed, if it appears on the other side, then it's going to be a virtual image. So once again, the first case, if for the object is placed between the center and the focal point, the image that is formed is beyond the center, inverted, and enlarged. In our second case, we now place the object beyond the center. So what's going to happen? As you can see from the diagram, we're going to have the formation of a real image that is going to be between the center and the focal point. It is going to be inverted, so that means it's going to be opposite to what the position of the object. So it's going to appear upside down, and it is going to be smaller than the object itself. So once again, if the object is placed beyond the center, the image is going to form between center and the focal point. It's going to be inverted, and it's going to be much smaller than the object. And obviously the third case is now when the object is between the focal length and the mirror. When the object is between the focal length and the mirror, the image is going to appear to be virtual, meaning it's going to be on the other side. It is going to be upright, and it's going to be enlarged. Once again, if the image is between the focal point and the mirror, the image is going to be virtual, meaning it's going to appear on the other side, enlarged, and upright. Please, you must absolutely, it's imperative that you memorize all three scenarios. One example of this is, as you can see in front of you, is makeup mirrors, and they obviously produce a much larger image, a virtual image, and you can see obviously, and you can apply basically makeup. Another application is, of course, digital readout devices that appear in cars, and you can see how the image forms right in front of you. Thank you so much. I'll see you in class.